Hi, this video introduces our work, learning category-level last-meter navigation from RGB demonstrations of a single instance. We aim to bridge the gap between navigation and manipulation. Mobile manipulation requires not only reaching an object, but positioning the robot's base precisely enough for downstream manipulation policy to succeed. However, most RGB-based navigation systems define success as stopping within about 1 meter of the goal. This level of accuracy is often insufficient for downstream manipulation, causing frequent execution failures. In this work, we study last-meter navigation, the stage between global navigation and manipulation. Unlike global navigation, which only needs to reach the vicinity of a target, last-meter navigation requires centimeter-level translation accuracy and degree-level orientation alignment. This precision is critical because manipulation policies are most likely to succeed when the robot's base pose lies within the distribution of their training demonstrations. With this necessity in mind, our approach operates under two primary constraints. First, we use only RGB observations, without depth, LiDAR, or maps. Second, we train from demonstrations of a single object instance and evaluate whether the learned policy generalizes to unseen instances of the same category. In our setting, we assume that the target object remains visible and that there are no occluding obstacles throughout the trajectory. This allows us to isolate the problem of precise robot-based positioning from global navigation. We define the task as goal-conditioned navigation toward a manipulation-ready pose. The target destination is specified by two inputs, a goal image and a text prompt specifying the object. For perception, the robot relies on current RGB observations captured by 5 onboard cameras. This configuration provides a complete 360-degree view of the environment at every time step. As shown here, our model ingests these visual streams and goal specifications to predict a discrete navigation action, controlling translation along the X and Y axes, as well as rotation. In our architecture, we first use a frozen vision encoder and a text-driven segmentation module to extract semantic embeddings and masks from both the current and goal views. The masked semantic embeddings are then fed into the score matrix-based action decoder. Instead of implicitly attending between embeddings, we compute a dense similarity matrix between masked current embeddings and masked goal embeddings. This is the key insight. The score matrix preserves the 2D spatial structure of the scene. This explicit representation provides a spatially grounded signal that allows the policy to reason about relative pose and alignment. As the robot moves, this matrix provides a strong, interpretable gradient that guides the policy to minimize the pose error. As a result, the model learns geometric relationships from a single object instance and transfers them to unseen instances of the same category. To understand whether explicit object grounding is necessary, we first evaluate Deno-TXT attention, a canonical vision language baseline. This model relies on implicit grounding. It uses cross-attention to attend to the target object from the text prompt, without any explicit segmentation or object localization. As seen in these examples, the model cannot reliably disentangle the target object from the background or distractor objects. It fails to localize the target, resulting in random walk behavior. This confirms that in low data regimes, implicit visual grounding is insufficient for precision tasks. Next, we ask, is explicit score matrix representation necessary? We evaluate Deno attention, which uses the exact same segmentation module as our method, but processes the embeddings using standard cross-attention layers instead of our score matrix. The performance improves. The robot can now find the object and succeeds on the training instance. However, it fails to generalize. When tested on unseen object instances, the standard attention mechanism struggles to capture the precise geometric relationship between the current and goal views. It often gets close, but fails to achieve the final centimeter-level alignment. This proves that knowing what the target object is isn't enough. The model also needs an explicit representation of where the target object is relative to the goal. In contrast, our score matrix method bridges this gap. It achieves strong success rates not only on unseen objects, but also in completely unseen environments, ranging from different indoor rooms to outdoor settings. As shown in these examples, the policy robustly adapts to varying lighting and backgrounds without any fine-tuning. Our evaluation confirms that our policy consistently outperforms baselines in both geometric accuracy and visual facing, maintaining precise behavior across these diverse scenarios. In summary, we demonstrate that explicit object grounding combined with score matrix representation is the recipe for reliable, RGB-only last-meter navigation. While our current system assumes object visibility and relies on the quality of the upstream segmentation model, it offers a robust alternative to depth-based or map-based approaches. This work suggests that with the right spatial representations, simple RGB policies can achieve the high precision required for mobile manipulation. Thank you.